Hi everyone, my name is Laura Rodriguez and I am a JPL postdoctoral fellow working with Dr. Lori Barge. Today I'm going to talk about some of my research, which is exploring the feasibility of using Raman-LIBS for ocean world exploration. So dual-LIBS Raman systems hold a lot of potential for planetary exploration as they enable the rapid accumulation of data from samples that aren't even necessarily close to the instrument. So they could be several meters, maybe tens of meters, depending on the system, away from the instrument. They also enable the analysis of LIBS and Raman of the exact same spot of any one sample. In fact, there is a LIBS Raman system already present on Mars via SuperCam, which is on Perseverance, imaged here. This work is actually part of a larger team effort to see how well LIBS and Raman does at characterizing the geochemistry of hydrothermal vents in situ. And so to that end, the team has built a spectroscopic payload dubbed Invader, equipped to do LIBS, Raman, and time result fluorescence. And here is one of the original mock-up designs of what Invader looked like, shooting a laser at a hydrothermal vent. Invader is going to be deployed to axial seamount, in particular to the Inferno vent system in 2022. So what is LIBS? LIBS is laser-induced breakdown spectroscopy. And the way that it works is it generates a laser that when it strikes the sample, ablates it into atoms, ions, and particles. The electrons within these species can absorb the laser light, get excited, and when they return to the ground state, they give off emission lines that are diagnostic of the elements present. These are actually the same emission lines that astronomers use when looking for elements in space. LIBS is really exciting because it is actually the only field technique that can detect all of the biogenic elements, which is important when you're trying to get at habitability or potentially looking for evidence of life. Some potential problems with LIBS include the fact that it's very sensitive to matrix effects, making it difficult to get quantitative information, and biogenic elements tend to also give off very weak signals. Raman spectroscopy works by you generate a laser when sometimes the energy from that laser can be absorbed by the sample due to molecular vibrations and rotations, and the returning light would be slightly shifted as a result, and that shift is called a Raman shift. So Raman's great for looking at organics and minerals. However, it does have some potential problems in that it tends to be a relatively weak signal compared to LIBS. A lot of darker materials, including iron minerals, which are abundant at vents, probably do give off poor Raman spectra and can dampen the Raman spectra of organics absorbed to them. And then you also have to contend with the issue of fluorescence overwhelming your signal. So the hydrothermal vent precipitate that I analyzed in this work is from the Herein chimney from Mothra Hydrothermal Field Endeavour segment, which is actually close to the field site where Invader is going to be deployed. So here's the coast of Oregon. We have our Invader deployment site, and here's where the sample was collected from. And here's an actual image of the Herein chimney before this part was knocked off, and we were given the top portion here, and that's what's imaged here. So I cut a column here and then cut that into even smaller pieces and then analyze the top plane of each using Raman and LIBS. And that was to see if we could get geochemical gradients as you go from the exterior of the vent, where you have ocean water, a lot of life, to the most interior, where it's really reducing conditions, no life, hot hydrothermal fluids. Both Raman and LIBS were conducted using a 1060 nanometer red energy fiber laser. With Raman, we doubled the frequency for that to 515 nanometers, and both systems were built by Impossible Sensing. So typically in an analysis, especially with LIBS, you choose a single peak that's diagnostic of an element, so for instance 393 nanometers for calcium, and you see how the intensity changes throughout the samples. But I was really interested in taking a multivariate approach, looking at the entire spectrum in its entirety. So those are the techniques I'll be talking about next. So focus will be on multivariate curve resolution, or MCR. And the way that this works is it's a deconvolution technique. So if you have like an overlapping peaks in the spectra shown here, it can deconvolute the overlapping peaks. And the way that it does that is it's looking at each of the peaks and seeing how they change relative to one another in the different samples. So for instance, those in yellow here, these 4 peaks, must have always been changing by the exact same amount throughout the samples, which means that they are all coming from the exact same component. Mathematically, the way that this works is you have a matrix full of your spectra. You break it into two different matrices, a C matrix, which is the matrix of the pure abundance of the components, and the S matrix, which is the pure spectra of each sample. And then E is your residual error. So the way that it works is it starts with an initial guess. For instance, you can start with C, and you hold that, and then the algorithm will alter S to minimize the residual error. And then once that's done, it'll hold the S matrix and it'll alter the C matrix to reduce the residual error, and then it'll keep doing that over and over. It is an iterative process. Another technique I looked into was partial least squares regression. I wanted to see if we could build a model that could predict the organic content in our vent samples. And the way that this works is it's modeling the covariance and the response variable here, the organic content, with an input matrix. And the result is a model that can predict the variable. To assess how well it does, you tend to look at a plot like this and see which is akin to a calibration curve to see how well the predicted values match up with the measured. And then lastly, I'll talk about low-level data fusion, and that's just where we took the Raman and concatenated it with the LIBS spectra and then used that as input for the PLSR model. So multivariate curve resolution, I'm first going to talk about that with the LIBS data only. The idea behind this is that LIBS is sensitive to matrix effects, so I thought potentially each mineral has its own unique mineral LIBS spectra, and that the components that come out of an MCR could correspond to that spectra. There's some precedence that this could work. So there was a paper by Haddad et al. In 2019 where they did MCR analysis of LIBS spectra of samples where they knew the exact amount of minerals that were present. But the big difference between that and what I'm trying to do is that paper, they knew how many minerals were present in each sample, and they had the pure spectra of each mineral. And they used both as a constraint in the MCR model. So they were really just focused to see if MCR could give accurate abundances. But the great thing about MCR is it's modular. So depending on how much you know about the sample, you can add that as a constraint to the model. If you don't know anything about the sample, that's fine. You can still do MCR. And so I was really curious, if you go in and you don't know anything about the sample, does it still give you a useful output? And so one of the first things you have to do for MCR is give it a number of components to use. But if you don't know how many to use, you could do a PCA analysis and then plot the eigenvalues which is essentially like the variance in the samples with increasing component. And so we see here that after about 6 components, most of the variability is explained. Increasing it does not improve the variability that's explained, really. And so then I did the MCR, and here are the results. So here is one of the MCR components shown in red compared with the LIBS spectra of barite. You can see there's really good agreement. Here's another example with MCR in red compared to pyrite in black. Once again, really good agreement. So it's showing that the pure spectra of the MCR is agreeing with the pure spectra of minerals. And so I was able to identify what minerals corresponded to the other components, and then I plotted their abundances based from the MCR results. So 0 is the most exterior of the vent, 30 is the most interior. And so that's plotted in black. And then I also plotted in red subsamples that we had sent out for quantitative XRD analysis. And then in blue is mineral analysis that was done via SEM of the Herein chimney by Crystal et al. In 2006. So it was a different part of the Herein chimney, but still the Herein chimney. In general, we found there was really good agreement between the MCR results and SEM and the XRD work. So for instance, barite here is the most concentrated in the exterior, rapidly drops off. And that's in agreement with the ground truthing. Pyrite is relatively depleted in the exterior and then, increases and kind of remains throughout, dipping off slowly as you get more into the interior of the sample. And you see that trend as well with the others. So the next I wanted to do was see if we could get a model that could predict organic carbon content. So to do this, I crushed up some pieces of the vent sample, made pellets with different amounts of organic mix doped in, varying between 0 to 32 weight %. The organic mix was a mixture of these organics shown here, and then their proportions are also shown. The these proportions and these organics were chosen to best reflect both the elemental and the macromolecular composition of a typical cell. So here's the results of doing PLSR with just the LIBS spectra of these pellets. In general, with the model that comes out is, it's pretty good. It's not the best. We got an R-squared value of 0.73, so it's okay. You can see that with increasing organic content, the model gets worse, and that's because, as you can see here, there's just a lot more variability in the samples. And you can see that when you do the LIBS analysis of these things, it was really hard to get a consistently good LIBS spectra. I had to analyze a lot of different points to get enough LIBS spectra to be used in this model. Here is the component from the PLSR that best explains increasing organic content. So you can think of this as a LIBS spectra with positive values being positively correlated to increasing organic content and negative being inversely correlated. So of course, in the positively correlated, we see a lot of lines corresponding to carbon. We got a nitrogen line, oxygen as well. Negatively correlated, you see a lot of the elements that are present in the mineral matrix. And that makes sense because as you increase the proportion of organic content, the proportion of the mineral matrix goes down. All right, so now we'll talk about the MCR analysis of the Raman spectra. So like the LIBS, the pure spectra were in good agreement with pure spectra minerals. So here is a MCR compared with Raman of barite, and it's in good agreement. Also shown is that comparing the MCR result with pyrite. Once again, that was in good agreement. With Raman, I actually was able to do mapping as well. So I plotted the MCR component corresponding to barite in this case to the maps of samples of the most exterior vent versus the most interior vent sample. And so what you see here is the most exterior, barite is present throughout. It's really enriched except for this vein here, where it's very depleted. And you can ignore the intensities here because they are normalized. So it's just important for giving a relative sense of concentration. The interior barite is depleted throughout. And these results are consistent with the MCR results from the LIBS data, which showed barite concentrated in the most exterior and then not present in the most interior samples. So here is the mapped out of the MCR component corresponding to pyrite. So it's depleted in the exterior except for this vein where it's enriched. And the most interior portion, it's pretty abundant, uniform throughout. And that's also in good agreement with the LIBS MCR results, which showed the same thing for pyrite. In fact, when we compare the two most exterior samples, we see something interesting. You see that there was a barite matrix, and there was probably some fluid intrusion where pyrite crystallized out. So they both agree very nicely to one another. And this just goes to show that, plotting out the MCR components can, reveal a lot of information about the sample, show you some interesting micro features. But also it shows that the abundances we're getting from the MCR are logical and make sense. So here is the PLRS of the Raman spectra. The model is a little bit better. We get an R-squared value of 0.85. Once again, as you increase the organic content, the variability between the Raman spectra increases. And that's because, for different reasons, but as you increase the organic content, you have more issue with fluorescence that just overwhelms the Raman spectra. And so here is the component explaining most of the variability in the organic content. So you can think of this as the Raman spectra. And of the positively correlated, this 1691 shift is really interesting because that tends to correlate with the carbonyl group. And a lot of the organics we dipped in had carbonyl groups. And then lastly, we did PLSR of LIBS and Raman fused together. We can see that it improved the model. So now we're getting an R-squared value of 0.9. So definitely fusing the two it was better than doing either technique alone. And actually now we can start trying to take this model, maybe after doing analyzing a few more points between 0 to 32 weight%, and use that for our analyzing our samples. So in conclusion, LIBS and Raman revealed geochemical gradients of ocean world analogs. MCR was a really powerful technique to not only deduce what minerals are present, but their actual abundances. And this was confirmed with ground truthing. And it was consistent between MCR of Raman versus LIBS. Mapping the MCR component gives you more information than if you just mapped a single peak. It can reveal mineralogical and redox hotspots. So barite is a sulfate, for instance, and you saw the pyrite vein, which is a sulfide. And lastly, the data fusion did enhance the analysis. So in future analysis of the PLSR model. So in future work, I would like to take that PLSR model and actually apply it to all of our vent samples to predict the distribution of organic content, and then ground truth that with gold standard techniques. And I'd also like to analyze these samples using Raman and fluorescence, or using the Invader payload, which is capable of time-resolved spectroscopy. So I would like to give thanks to those that have helped me throughout this project, especially my postdoc advisor, Lori Barge, the OHL lab group, and Pablo Sobrón, who is the PI of Invader. I'd also like to thank the Invader team, without which this project would not have been possible. And thank you for your time and attention.